we ended up drawing this compound. Emma Lee, can you remember, did we finish finding the formal charges on this compound when we were done with it? HCN? Do you remember, Emma Lee? Did we finish finding the formal charges on that?
Let me check.
Or is that where we left off? Maybe we didn't leave off there.
I don't think we did those two yet.
We didn't do either of these two?
I don't think so.
All right. Well then, let's identify the Lewis dot structure for HCN. Okay. So what do we do first, Emily? Do we once we have this compound, we want to write its Lewis dot structure. What's the first thing we want to do?
You find which atom is the central atom.
Okay, very good. And what do we have to go off here? What do we know about these elements? Usually, Emily, we choose the one that there's the fewest of, but here all three are the fewest. I mean, there's only one of each. So how would you choose, Emily? Which one would you choose as the central atom? Oh, looks like we lost Emily. Harry, how do we know which one to choose as the central atom?
So certain atoms have certain tendencies, and in this case, carbon is usually the central atom.
Okay, very good. Let's go back a slide here. Carbon is generally, it says always here, I would say it's better said generally, will want to be the central atom. Very good. Another rule here is if there's more than one element contributing only one atom, then the element farther left and lower down on the periodic table is usually the central atom, or the least electronegative. And that rule would fit here as well, because nitrogen is more electronegative than carbon. So, carbon, nitrogen, hydrogen, whoops, I kind of skipped ahead. Well, I don't know if I did or not, but I made the central atom, put the other two atoms on the outside, and then I draw a bond. Okay, what's next, James Oliver? What do I do next when I'm drawing the Lewis structure of a compound? I've got my skeleton structure here ready to go. What's next, James Oliver? Are you there?
Yeah.
Any ideas? What's next?
I'd like to find the total amount of electrons it has.
That's right. Find out how many electrons were brought to this party, right? And what is it, James Oliver? How many electrons did carbon bring to the party?
5, right?
Well, here, let me bring up my periodic table. We can tell its location.
Oh.
How many?
4.
4. Carbon brought 4. Nitrogen brings how many?
5.
5. And hydrogen?
1.
1. Very good. So we have a total of 10 valence electrons. Very good. Okay, James Willis, what do we do next?
We give everything the appropriate number of valence electrons until we're out of electrons.
Very good. We have to, at this point, also be sure that we recognize that these two bonds, what are those two bonds? How many electrons is that, James?
4 total.
4.
2 each.
Yeah. So we need to recognize that we only have 6 valence electrons to move forward here. Okay. Catherine, are you up and running yet? No. Katie, tell me, now we have 6 valence electrons to distribute. Where did we say we want to go first? Do you remember, Katie?
We give them to carbon.
All right. And how many electrons does carbon need at this point?
It has 2, so it needs 6.
Okay, it has 2 sets, right? Which are each of those 2 sets contain how many?
4.
Yeah. So there's 1, 2, 3, 4. So we actually only need how many more?
4.
4. So we can add those as lone pairs, non-bonding electrons, right? All right. So I have 2 valence electrons left. Where am I going to go with those, Landon?
The 2 valence electrons are going to go to the outside.
Of nitrogen?
Yeah.
There we go. Okay, so I'm out of valence electrons, but I'm still not in a situation where all of my atoms have the appropriate number of electrons available to them, right? So, what can I do, Malia, to fix the situation? Did we get to this last class?
You can take 2 of the dots from carbon and make another bond going to, going to nitrogen.
Okay.
Or turn the 2, I don't know, some of the dots into a bond from carbon to nitrogen.
Yeah. Were you thinking maybe bringing these over? Is that what you're thinking?
Yeah.
But that would
That's good.
decrease the number of electrons around nitrogen, it wouldn't increase it, right? We need to get more electron density this way, right? Because carbon has plenty of electron density right now, but nitrogen doesn't have enough. Okay, so after we were to do that, then we would have a double bond there. Like that. Okay, very good. Is it Nikki's turn? Are we done here?
No, you have to add the 2 on top of carbon to another, like to do a triple bond with nitrogen.
Okay. Yeah, we need one more bond there. Okay. And we know this because nitrogen needs to have available to it 8 electrons. Now we're in a scenario where carbon, how many electrons are available to it, Precious, right now as it's drawn?
8 electrons?
Yeah, 8 electrons are available to it. And this nitrogen, Samantha, how many are available to that nitrogen? How many electrons are available to it?
8.
Yeah, 1, 2, 3, 4, 5, 6, 7, 8. Very good. Now, Stratton, what's the next thing we do to make sure that this is the good electron configuration?
I'm not quite sure.
Okay, it's right here. Remember this slide? Formal charges are formal charges, right? Which are the difference between the number of electrons that it brought to the party minus the number of electrons that it has not available to it, because all atoms are going to have 8 available to them. Unless it's hydrogen, then it's going to have 2 available to it. But minus the electrons that it has right around it. Okay? So, Taewon, how many electrons did carbon bring to this party? Kim, Taewon, are you there? You can type it down below if you want. How many electrons did carbon bring to the party?
4.
4, that's right. It brought 4 electrons to the party. And how many does it have right around it? Do you know how to determine that, Taewon?
8.
Yeah.
Is it 8?
Oh, it has 8 available to it. But when we want to determine formal charges, we take the 4 that it brought and we subtract how many are right around it, which is 1 here, 2, 3, and then 4 electrons right there. So that's how we count up how many electrons are right around an atom. The bonds act as a single electron. So then 4 minus 4, that tells us that our formal charge, Fc, is equal to 0. All right. Does that make sense, Taewon?
Okay. Yeah.
Okay, good. How about the nitrogen, Emily? What's its formal charge?
So it has, does it have 5 right around it?
That's right. 1, 2, 3, 4, 5. So how many did it bring to the party?
5.
Yeah, so it brought 5 minus 5. So its formal charge then is also 0.
Okay.
The formal charge on the hydrogen is 0 as well. It brought 1 electron to the party, and it has just 1 electron right around it. All right, so what that shows us is that this is a stable electron or Lewis dot structure. All right, so that is a good representation of what the molecule looks and behaves like. Okay, very good. Now we're going to, again, we followed our rules. We identified the central atom. We created the skeleton structure. We counted up the number of valence electrons, and then we filled up the central atom and then tried to adjust so we could fill up the other atoms. All right. And when we were done, we identified the formal charges on all the atoms. Okay, so those are our steps. And I'd like you guys to break into groups now, and we'll do the Lewis dot structure for this compound here. PCl3. All right. So before we break into groups, let me tell you that when you're in a group, a little breakout group, one person will be designated, I think it's the person who shows up first, as the presenter, and that presenter will have access to a little bar to the right side of the screen where they can allow everybody to write on that screen. Now, I can't figure out how to get rid of everything on that screen. You can erase it, but it's not worth it. You can just write right on top of that, and then you guys can work on the Lewis dot structure for this right on that screen. Okay, I'll come into the groups and try to help you if you're having trouble, but so you should be able to write the actual Lewis dot structure onto that screen. Okay, so here we go. We're going to go into our breakout rooms now and draw PCl3.
You are currently the only person in this conference.
James Oliver, it looks like you are the presenter. Figured it out? Very good. Excellent. Good.
Multi-user whiteboard. Draw it together. There you go.
All right. How do you make it white?
Yeah, I don't know how to make it white. Can't figure that out yet. But it's okay. We can see right on top of it. Good job, guys.
Okay.
But like, I don't know how you do, because there's 3 chlorine atoms and only 1 phosphorus.
So I think you would put it one up and then another one here, another one here.
Yeah.
And then we got Cl, and then 1 down.
Yeah.
So it'd be evenly distributed.
Sure.
Perfect. Okay. And then
Now muted.
phosphorus has a plus 5 star, or electron is 5, and then Bl is 7, right?
Yeah.
And there's 3 of those.
So there's 3. So there's 21, and then phosphorus has 5, so it'd be 26.
Yeah.
Welcome. In this video, we're going to show you how to use Big Blue Button as a moderator and presenter capabilities. First thing is you'll see you'll be invited to join the audio, just as the viewers. I can join listen only, but I'm going to join the users list. When you join as a moderator, you have a square, but you can also click and you can mute them as well. You may also see students join listen only. When students join listen only, they can't talk, but they can hear you as well. Students can also set their status, which means their initials will be replaced by other moderator capabilities. I can mute all the users. I can mute everyone except myself. And I can also lock the viewers down as well. So this means I can prevent them from sharing webcams, sharing microphones. I can drag and drop a student between each room, breakout room, just like the students. You can join the audio, you can see the students in the room, and when you're done, you just close and you're back to the main room. At some point, you may wish to end the breakout rooms before the end time. You just click end. I'll rejoin the audio. And we're back in the main room. Students are all back, ready to pick up where you left off. Let's turn to the presentation area. Here, by default, the whiteboard tools are selected, so I can use the pen tool to draw. I have a series of tools here as well, which I can use. So let me go to a blank slide. If I want to draw, I can do a little bit of drawing. And as the instructor, I'll draw will be frozen. I can bring this up, I can browse my files, and here I've got something ready to go. This slide has E. Let's say I want to do a poll. I'm going to ask the option here. B, C, and D. Let's say I want to be efficient to share a presentation because it only downloads once to the user's computer. Unlike trying to share your desktop, which we'll show in a moment. Here the slides have A, B, C, and D. Let's say I want to do a poll. I'm going to ask the students, what is the result? Because it's actually formatted just fairly simply, Big Blue Button actually realizes that you'd have a poll for A, B, C, D. You also have the polling option here, and I can choose A, B, C, D. So if I do it, the students are all presented with a poll. I can see there's one response, and I can publish the results. When I'm done polling, I just close the poll. And then I can clear the polling marks as well, because they're just whiteboard. If I want to share YouTube video, I click here, choose Share YouTube Video. I have a URL ready to go. Just click it, I do Share Video. Presentation area will become the video, and it will start playing.
Okie dokie. So, looks like we're almost all here now. Where did we leave off? Anybody know whose turn it was? James Willis, why don't you tell us how it went in your group?
In our group, we did pretty okay. We got. Oh, can I draw?
Yep, go for it.
So it was phosphorus trichloride, right?
Yep, PCl3.
So we got phosphorus in the middle, and then the chlorines, and then one bond between each of them, and there's a total of 26 electrons.
Okay.
6 of which are already accounted for in these bonds here. And then if you just put in the electrons, there's no more bonds, because that adds up to 26 electrons, and then everything has a formal charge of 0, because phosphorus brought 5 of them, and each chlorine brought 7. And if you count, there's 7 electrons right around each of the chlorines.
All right, very good. So we did need to make sure that we had those 2 electrons on phosphorus, right?
Yeah.
Excellent. Okay, any questions? Okay, so then let's try to draw the Lewis dot structure for carbon dioxide, following this kind of the same pattern that we've been following here. Katie, carbon dioxide. What's our central atom?
Carbon.
Carbon. Very good. So I write down the carbon. I draw 2 oxygens around it. Right. Landon, How many electrons, valence electrons, are in this party?
Four. Hang on 1 second. 6, 12 plus 4. 16.
16. 16 valence electrons. Malia, how many do I have already on there? Shown in my
You
skeleton.
already have 4.
I already have 4. All right. After I've got 12 electrons to distribute, Nikki, where would I put them next? Who needs them first?
You put them around carbon first.
How many do I need there?
Oh, you need 4.
Okay, very good. All right, Precious, where should my next electrons go?
To the oxygens.
All right. So how many does this oxygen need? How many electrons?
6.
6. 1, 2, 3, 4, 5, 6. Now it has 8 available to it. Okay. Samantha, my other 2 electrons are going to go here, right? Now what's my problem with this molecule that I have so far, Samantha? What do I need to do here? What can I do to fix this molecule, Samantha? You there? Let's see, I'm not looking at the chat. Oh, she can't use mic. Okay. Stratton, you available? You want to tell us what you would do next here? Or if you want to type something, Samantha, go for it. You need to move electrons from the bond to form a bond with the oxygen. Turn electrons into bonds. Very good. So coming from our carbon here, if we turn those into a bond there, right, and create this. All right. Taiwan, are we missing electron density anywhere? Do all 3 of these have 8 electrons available to them, Taiwan?
What was the question?
How many electrons does this carbon have available to it?
It's 5.
Well, it has 1, 2, 3, 4, 5 right around it, but how many does it have available to it? When we're wondering how many it has available to it, we count each bond as 2. So here it's 2, 4, 6, 7, 8 electrons available to it. How about this oxygen, Taiwan? How many electrons does it have available to it?
6.
6. So we're not quite done. We need it so it can have 8 electrons available to it. Do you know how we can fix that, Taiwan? How can we get more electrons available to that oxygen? Like we did here, we brought in electron density. We're going to have to do the same thing like that, right?
Okay.
Okay. So 1, 2, 3, 4, 5, 6. Whoops, I got some bleed through there. Let me draw my compound over here. Okay. Does everybody have 8 available to them, Emily?
Yeah.
Yeah, everybody has 8 electrons available to them. So what do I do next, Emily, to determine whether or not this is a feasible compound?
You would figure out the formal charges.
Very good. What's the formal charge for this oxygen here? And Harry, why don't you figure out while she's doing that, you think about the formal charges for this oxygen over here. What do you think, Emily? What's the formal charges for that oxygen?
It would be 5 right around it. 5
Good.
right around the oxygen,
That's
and
right.
it brought.
So bring up my periodic table here. How many electrons did it bring to the party?
6.
6.
So it would be 1.
Yeah, a positive 1 formal charge. Harry, did you determine what the formal charge is on this oxygen?
Yeah, so oxygen has 6 valence electrons. It has 7 around it, so the formal charge is -1.
-1. Very good. So something's not right, correct? James Oliver, what's the formal charge on our carbon?
4.
So it brought 4 electrons. And
All formal charges.
yeah.
It would be 0, right? Since there's 4 bonds.
That's right. So carbon dioxide, the chemical formula, CO2, there's no charge on carbon dioxide. So the sum of all the formal charges should add up to what that charge is, which is correct here, right? But the distribution of formal charges like that indicates that there's a problem. So we have to, the negative sign means there's more electron density than there should be around this region of the molecule. And the positive sign, what do you think it means, James Willis?
That the electron density is lower than it should be.
That's right. So how can we fix that, James Willis? What can we do to fix the electron density distribution here?
We can take one of the lone pairs from the left oxygen and move it over to the right oxygen, and take one of the bonds from the right and move it to the left.
Okay. That's a lot of moving. You're saying move this over here like this and move this over there like that?
Yes.
Right? Now, electrons don't hop outside of the molecule like that. So that is ultimately correct, but I think that, here, let me give myself a little more space here so we can see what's going on. I think that what we would kind of want to imagine happening here, or recognize that the flow of electrons is going to go like this, where we have these electrons come into this bond, and these electrons go out onto that oxygen there. Does that make sense? So now we have oxygen and 2 lone pairs there, and we have this oxygen with another bond there, and then the 2 lone pairs like that. That's what you're looking for, right, James?
Yes.
All right, Katie, how are our formal charges now? What's the formal charge on this oxygen, Katie?
0.
0. That's right. And this oxygen is in the same condition, so it's 0 also. Our carbon, is it still 0, Landon?
Yeah.
Yeah. All right. So we have a good Lewis dot structure, right? A good Lewis dot structure. Very good.
I have a question.
Yeah, go ahead.
So when we first started this problem, there were 8 valence electrons that needed to be distributed between the 2 oxygen. Couldn't you just split that up and put 4 on each side, and it would be a lot cleaner than what we just did?
Yeah, it just depends on, so we do, I mean, the flow of things usually doesn't find any potholes if we fill the central atom first. All right, we can get to, all right, we got there just fine, and it taught us some lessons about formal charges, and using formal charges is important. Finding symmetry is nice, but we don't always know that that's exactly what should happen. And if we just kind of let symmetry guide things, it's fine, but we always have to use formal charges to make sure that we get that the formal charges are driving the process, right? Again,
Right.
Symmetry is nice, but formal charges ultimately need to be the thing that kind of direct us through the process. But you're right. Depending on how we distributed our atoms, we could have got there a lot smoother.
Okay.
Okay, so then, let's talk about this situation, okay? Some compounds, not many compounds, have what's called an expanded octet. An expanded octet. Expanded, meaning more, octet, 8. So that means that a central atom can actually have more than 8 electrons around it. All right. So why or how can this be? Well, it turns out that if your element of interest, the central atom, is in the 3rd row or lower, all right, so if we're looking here at the periodic table, 1st row, hydrogen and helium, 2nd row, 3rd row or lower, phosphorus, sulfur, chlorine, argon, or lower, these nonmetals as central atoms can have more than 8 electrons available to them and still result in a stable compound. Okay? And the reason that is because that 3rd shell that those electrons are in have d orbitals, and those d orbitals have space for additional bonding to occur. Okay? So let's look at an example of a compound like that. It's this sulfur hexafluoride. If you think about the central atom there, sulfur, and then the 6 fluorines on the outside, immediately you would see that we're going to need multiple or more than 8 electrons to be available to that. Okay, so let's also watch this video here where they take some of this sulfur hexafluoride, right? And they're going to put it into a box here. All right, this box, like a fish tank sort of thing, covered right now, but we're going to uncover the box, and then we're going to put this tinfoil boat, basically it's a tinfoil box acting like a boat, and it's going to float on top of that layer of sulfur hexafluoride. So much more dense than air, acting like a liquid in there, but it's in the gaseous phase, so we can't see it. All right? Another very interesting thing about this material, you already saw that, hey, you could breathe it, right? I mean, that guy breathed it. Not that I would recommend it. You can't breathe helium very long without dying. And same thing with anything that, you know, might not react in your lungs, but it's not going to give you oxygen, so, you know, you can't do it very long. But another thing here, we'll show what he does here.
All right, so look, so here's a taser. So when I put the taser down, conduct electricity. So here's a taser. Okay. Yeah. All right, so look, so here's a taser. So when I put the taser down inside here, watch this. When I put it down inside, it stops.
Oh, it stops working.
And then when I bring it back out again, so they will keep it. So if you don't want something for arcing from one place to another. But the coolest thing is this: because it's inert, you can breathe it, and you might see something different. Ready? So just stick your head way down and breathe in it. Breathe in it. Ready? Now talk to the nice people. Try it. Come here.
Okay, so similar effect, and the inertness of sulfur hexafluoride also, can be predicted by its Lewis dot structure, right? And so like I guess we kind of skipped over the part, but they use this in making of many electronics, because what it does is prevents unwanted electrical arcing from occurring. So when they're making microchips and so forth. So it's a very interesting material. It's an example of being able to recognize and predict the properties of a material based on its Lewis dot structure. So let's go over here and draw a Lewis dot structure then. Let's see, how do I do this? I thought I could clear everybody's. There we go. All right, here we go. Whose turn? Katie, Landon, Malia? Is it your turn, Malia, or was it? We'll go with Malia. Malia,
Yeah,
why don't you draw? What's that, Malia?
It's my turn.
Excellent. Why don't you start drawing for us the Lewis dot structure for SF6? I'll write SF6 over here in the corner. All right, so we got sulfur as the central atom. Now, there was probably one obvious reason that sulfur was chosen, because it's the one that there's the fewest of, and that's fine. Is there another reason why we might not have chose sulfur while she's finishing that up? Nikki, can you think of another reason why we knew fluorine wasn't going to be a central atom?
Because it is more electronegative.
Very good. Fluorine's more electronegative. And specifically with this expanded octet model, what's wrong with fluorine in terms of an expanded octet, Precious?
It already has 7 electrons.
Well, because fluorine is only in the second row in the periodic table, it can't have more than 8 available to it. Does that make sense?
Yeah.
Okay, everybody, let's try to fill in the... Well, so how many electrons do we have, Malia? How many are in the party, and how many do we have on the board?
On the board, there's 12.
Okay, so subtracting 12 from the total, how many did we start with?
There's 6 for sulfur and 7 for phosphorus.
7 for fluorine. So that's 7 times 6, is that right? 42 plus 6. So, what's that?
48.
Okay, so we got 48.
36.
So we have 36 left over?
Yeah.
All right. Okay, where are they going to go? Should we all fill it in for her? Everybody, work together. Let's fill this thing in. All right. Excellent. Now, the formal charges. What's the formal charge for our fluorine here? Nikki, what's the formal charge for each one of these fluorines?
It would be 0.
That's right. And Precious, for the sulfur?
It's 0.
That's right. 6 electrons right around it. It brought 6, 0. So we got a happy compound, right? So let me show you something here. Sulfur, 6 regions of electron density. We can think of those as kind of on X, Y, and Z planes, right? And the fact that you end up with a very symmetrical molecule 3-dimensionally, even though, you know, fluorine gas, my goodness, probably the most deadliest thing that exists out there, fluorine gas. Sulfur, you know, you can't breathe sulfur by itself, but this compound, because of its symmetry and because of its equal distribution of electron density, the compound's nonpolar, the compound's very inert. All right, so the properties it has are described to us by looking at the Lewis dot structure.
For any of the elements that are the central element, when they're in the third row or they're following the expanded octet rule, you don't add any more dots to them, right? Because they already have a lot of electrons with them.
If there are extra electrons, that's where you would add them, to start off at least. And again, so yeah, if we had extra electrons, we would have put more on the central atom, and then we'd have to kind of use our formal charges to figure out if that's a correct placement of those electrons. So here's an example. Here's an example. XeOF4. Let's work on this one together. XeOF4. Where did we leave off? Stratton, I think it's your turn. Or did we give? I think. Did you say anything, Samantha? Is it your turn or is it Stratton's turn?
It's my turn.
All right, Samantha. Why don't you give us your best guess in terms of what you think the central atom would be on XeOF4? Drawing a Lewis dot structure here. XeOF4. What do we think? What's our central atom?
Would it be the Xe?
Xenon. Why are you thinking it's xenon, not oxygen?
Would xenon be more electronegative than oxygen because it's lower on the periodic table?
Okay, so it would actually be less electronegative. That's right. That's a good reason. Very good. What's another reason we might want to choose xenon, Stratton? Less electronegative. What's another reason in this case? What would be wrong with this skeleton structure? 1, 2, 3, 4. Anything wrong with that, Stratton?
Would it be because Xe wouldn't get enough electrons?
Well, we would fix that up as we added up electrons and stuff. We're not done. This is just a skeleton structure. But there's something else that's sticking out. Taewon, can you see it? What's wrong with this structure here?
Oxygen brings too many electrons.
Oxygen, yeah, oxygen here can't have, what do we call this, where it has more than 8 electrons available to it? What do we call that? Was that you, Stratton?
Yeah, I'm not sure what that would be called though.
Okay. It's called, Taewon, do you know what it's called when we have too many electrons available to it? I mean, more than 8 available to it? Taewon? Kim? Yeah.
Octet.
An expanded octet. Good. An expanded octet. And oxygen. Can oxygen have an expanded octet, Taewon? The periodic table tells us, right? Oxygen can't have an expanded octet. How do we know that, Emily?
Is it because it only has 6 valence electrons?
Harry, do you remember why oxygen can't have an expanded octet?
It doesn't have a d orbital, so it's not capable of holding more than 8.
That's right. So it's only in the second row here. No d orbitals, no third shell yet. So you have to be in the third row or lower to have an expanded octet. So good. 2 reasons we know that xenon has to be the central atom, right? Xenon has to be the central atom because it has to have enough space to hold an expanded octet, and it has to have, and it's less electronegative. Okay, very good. So here we are. We're going to finish this up together. James Oliver, can you tell me how many electrons are in this party? Everybody add them up. See if you get the same number. What'd you get, James?
I'm still kind of doing the math right now. So,
all right.
Yeah.
Xenon brought how many? James Willis?
Xenon brings 8.
8. Oxygen, Katie?
6.
6. Then the fluorine, how many did the fluorine bring, Landon?
Fluorine brings 7, but in this case it brings 28.
Yeah, 7 times 4 are 28. What is that? 36 plus 6? Is that 42?
Yep.
Okay, Malia, how many electrons do we already have on the board?
10.
10. So just 32 more. Where do we go first with our electrons? Is the central atom okay, Nikki?
Is it more than okay? Because it has more than 8.
Yeah, it has more than 8 right now, so we don't need to necessarily put any more. So why don't we start with, I don't know, 32. That would be 6 for each of these, right? 1, 2, 3, 4. Wait, 1, 2, 3, 4, 5. 6 times 5. No. Yeah, 6 times 5. If every one of these got 6, whoops. That would use up 30. And then where would we put the last 2 electrons, Precious? What would we do with the last 2?
I'm not really sure.
Okay. Well, and that's what Nikki asked before. Did you remember what I said, Nikki? Where would we put these last 2 electrons?
You would put them with Xe.
That's right. We'd put them on the central atom.
Do you just put them as dots like that, or could you, or like, would you form a double bond with one of the other atoms?
Well, that question would have to be answered with formal charges, right? So this is where we would put them just to start with, and now we have to go through and analyze our formal charges and see where we need to shift electron density around to. Let's see, Samantha. Do any of these atoms look like they have formal charges other than 0?
Would it be the oxygen or the xenon?
I don't know. Is there any? What's the formal charge for the oxygen? How many electrons did it bring?
It brought 4.
No, it didn't bring 4 to the party. It brought, you can look at the periodic table here, right? It brought 6 to the party, right? Because it's in the 6th column. Does that make sense? Okay, good. 1, 2, 3, 4, 5, 6. So it brought 6 to the party. All right. And how many does it have right around it?
Has 7.
7. All right. So it's going to have 6 minus the 7, -1. So right now it has a -1 formal charge around that oxygen. That means what about that oxygen? Let's see. Is it Stratton's turn? What does that tell us, Stratton? What does that -1 tell us?
Would it be that it's short 1 electron?
No, it means it's a negative charge. It means there's too much electron density. Okay, Stratton, what's the formal charge on the xenon? Is it 0? Everybody look, what's the formal charge on the xenon? How many did it bring?
It brought 8.
Brought 8. How many does it have right around it?
7.
7. So we're getting a positive
+1.
1 charge there. All right, so we need to move electron density around. What can we do? Emil, or Taewon, what can we do for our electron density?
Making a bond.
Yeah, making a bond from what electrons? From electrons from oxygen or electrons from the xenon?
From oxygen.
Of oxygen, that's right, because we need to reduce the amount of electron density here and bring more down here. Okay, so if we do that, right? Our formal charges are all 0 now. And so that tells us that, or got all our valence electrons on there. So it tells us that this is a stable, a good representation for a Lewis dot structure. All right, very good. If you have time to, and if you're planning on taking 106 here, I'm going to clear the chat window. Please let me know, say yes or no if you're planning on taking 106 next in the spring here. So yes, I am. No, I'm not. How many people are going to be taking 106 in the spring? So we got 1, 2, 3, 4, 5 people. 6 people. So if I could speak with those people and try to get their ideas, their feelings about some questions about efficacy in terms of teaching and interacting online, that would be great. Everybody else is welcome to leave. If you want to talk about something else, you're welcome to hang around. But other than that, I'll see you guys on